Hi everyone, I'm Ben. We're Team Alpha. Today we are going to present how we apply machine learning in Bitcoin arbitraging. Our presentation will have 4 parts. First, I will briefly talk about why we are motivated to do this project topic and the problem that we are trying to solve in this project. In the second part, my teammate Terry will introduce you on the data that we work with. And in the third part, the machine learning model that we deployed will be presented in detail. Lastly, I will give you an idea on how we backtested our model and the result from the backtest. Okay, now let's move to the first part, motivation and problem description. You might know there are many different Bitcoin exchanges where people can buy and sell Bitcoin freely. However, you might not be aware that these exchanges often have a price gap to each other. Here are some screenshots showing the Bitcoin market price in different exchanges. You may notice that they all have different market price, and some of them have a large price gap. This allows us to profit from arbitraging between exchanges. Indeed, there exist many arbitrageurs in the market. Now I will introduce their typical way of arbitraging to you. At the beginning, the arbitrager will hold same amount of Bitcoin and cash at 2 exchanges. If there exists a price difference between exchange A and exchange B, the arbitrager will buy Bitcoin at the exchange A, where the Bitcoin is traded at a lower market price. At the same time, the arbitrager will sell the same amount of Bitcoin at exchange B, where the Bitcoin is traded at a higher market price. At the end, the total Bitcoin holdings in 2 exchanges don't change, but the total cash balance will increase. In this case, the cash balance increases by $2 after the arbitraging operation. Assuming Bitcoin price being constant through this practice, the arbitrager gains $2 profits at the end. It sounds easy to do an arbitraging, right, from above a process, but things get complex in reality. First, the price gap between 2 exchanges often fluctuates. The first thing that the arbitrager to consider is whether the price difference will persist in next moment. If the price difference will be closed in the next moment, but the arbitrager still executes an arbitraging operation, she will likely lose money on the commission fee charged. In an even worse scenario, where the price difference between 2 exchanges will be reversed, the arbitrager will suffer a huger loss. Second, arbitrators must consider transaction fees, as she has to repeatedly perform the arbitraging hundreds and thousands times. The transaction fee per order will add up to a large number that cannot be neglected. Third, we need to consider the gaming among arbitrageurs. If there are already many arbitrageurs, every price gap will likely to be closed very soon. In this case, if you still want to profit from arbitraging, you have to adjust your arbitraging strategy. For example, you might have to lower your ask price so that your sell order can be executed faster than other arbitrageurs. Thus, you can complete arbitraging faster. In our project, we will apply machine learning to address these 3 concerns. We build up 2 machine learning models that can predict the price difference and handle its fluctuations. We also designed and backtested a trading strategy that includes considerations on transaction fees. Finally, we explored how our model can help in coping with the gaming among arbitrageurs. Now, my teammate Terry will brief you on data that we use to build our model.
Thank you, Ben. Let's talk about the data first. I will explore the data through the graph. First, we will use real-life data from 2 Bitcoin exchanges, which is Wire Exchange and Stamp Exchange. As we can see in the graph on the left-hand side, it shows the price difference on fire and stamp Bitcoin exchange. And we can observe that the price difference is very small between two Bitcoin exchange. Also, we can see the graph on the right-hand side, which is the price difference percentage, and it shows a big fluctuation when there is a drop or spike in the Bitcoin market. For example, there is a sudden drop in Bitcoin price between September and October, and we can see that the price difference percentage on that period is significantly high. Every time there is a fluctuation, the price in big exchange will first react and reflect the fluctuation. Then the small exchange react and reflect the fluctuation. So the net in reacting to the fluctuation causes the price difference. In order to export the data, we use the distribution plot to perform the univariate analysis. Here we can see the stamp and fire volume, which is the total transaction volume in the Bitcoin exchange. And we can see the size of stamp exchange is bigger than the fire exchange, as the maximum transaction volume in stamp is 7,000 and the maximum transaction volume in fire exchange is 200. After we conduct the univariate analysis and we start the bivariate analysis, we use the heat map to find out the relationship between different sets of data. The heat map and the table shows the positive and negative correlation to the Bitcoin price difference. Fire price, stamp price, Pareto index, and XBT/USD is a positive correlation to Bitcoin price differences, and it shows the orange color in the heat map and red color in the table. Fire volume, stamp volume, Europe to USD exchange rate, USD to CNH exchange rate, gold price, fire variance, and stamp variance is a negative correlation to Bitcoin price differences and shows the red color in the heat map and blue color in the table. After we conduct the bivariate analysis, we can get several results. First, we can use the positive and negative correlation to predict the price difference. Because, for example, in positive correlation, it means when the future in positive correlation is increasing, the Bitcoin price differences will increase at the same time, so it is useful for us to conduct forecasting. Second, after we conduct future selection, we will delete the most irrelevant feature. So we will select Cycle Index, XBT/USD, Europe to USD exchange rate, USD to CNH exchange rate, and gold price to conduct the future engineering. As they are high correlate to Bitcoin price differences, so they are useful to predict the output and conduct the future engineering. Third, as fire variance and steam variance is very close to zero, which is very low correlate to Bitcoin price differences. So we will not use these two features to predict our output. Let's pass the time to Marcus to talk about the Alama and US LSTM model. Thank you.
Thanks for the terrorist introduction. Now let's move on to the model parts. Nowadays, there are many different kinds of ways implemented about the economics variables like Bitcoin price, stock price, and so on. And as for the methods, there are four mainstream methods according to the bibliography. The first one is affection analysis based on the natural language processing. And the second one is intelligence method based on the expert knowledge base. And the third one is the economics prediction based on the micro factors. And the last one is the statistics method based on the machine learning method. So here we only choose two of them to finish our assignment. The first one is the ARIMA combined with the LSTM. The ARIMA is known as fitting data with a high linear attributes, and the formula shows the Q means the sequence is linear correlated with the previous Q time lag. However, it is impossible that the real data is pure linear with some other factors, and there is also nonlinear part of the series. So we also want to use the LSTM to fit the data. LSTM is known as its nonlinear fitting ability, and according to the special structure of the neural network, it can also adjust how long the memory will last. So the way we decide to combine, and for the way we decide to combine with both of them, is that we first used ARIMA first and then generate residues and put the ARIMA residue as input to do the LSTM training. The aggregation of the ARIMA prediction value and the LSTM prediction value is the overall prediction value. Here is the experiment data results, and we get the statistics results. For the ARIMA part, the residues are almost obeying the normal distribution, but for the LSTM, after different training, almost every R2 is between 15% and 25%. It is not very good performance. But the overall result is a little bit satisfying. Then we use the 4 matrix to evaluate the model: MAE, MSE, R2, and accuracy. We can see that the ARIMA and the overall model have the similar R2. That is to say, in regards to the R2, the overall model doesn't have any improvement. But for the accuracy, the overall model can improve the accuracy by 10%. So we can know that maybe sometimes predicting the exact series value is difficult. We can choose the movement to be our target, just as one represents going up and zero represents going down, or even more levels of the two represents going up in a large degree, and one represents going up in a low degree. So we can use the movements as our target, and it is also useful for the real policy and easier to conduct. Bitcoin, and besides, Bitcoin service is majorly made of linear parts, because you can see the ARIMA. We only use ARIMA, and it can get some. It can also get some good results, but the LSTM did not. So we think Bitcoin servers have very little nonlinear parts. Now let me introduce another group mate, Kellen, to introduce her model.
After the previous trial of combining ARIMA and LSTM, in this experiment we are taking a pure machine learning approach, which is employing an XGBoost model. This model makes several important modifications on gradient boosting model and usually has higher training efficiency and model performance than traditional tree-based models. We first did feature engineering, then we built 2 baseline models and the XGBoost model. Finally, we evaluate those models and compare their performance. In the feature engineering part, as Terry just mentioned in the data exploration, we first delete the features with over 20% missing data and delete the most irrelevant features according to the correlation metrics. And finally is the most important part of feature engineering, which is time lag feature creation. We slide the 1 hour time window for 8 times to create 8 new time lag features for price difference, and all other features are shifted back 1 hour. So finally we got 17 input features in total after the feature engineering, including 4 aggregate features in the exchanges, 5 features regarding the macroeconomics development, and 8 time lag features for price difference. Using those input features, we build 2 baseline models using decision tree regressor and random forest regressor. And the performance of each model is evaluated using 4 types of evaluation metrics, which are R-squared in terms of the whole dataset, the classification accuracy, and the R-squared in terms of positive and negative price difference separately. The 3 R-squared metrics measures the goodness of fit, while the classification accuracy measures the model's ability to correctly predict the sign of price difference. We trained and validated an XGBoost model. We did the following hyperparameter training via grid search and select the best parameters. We also defined an early stopping round as 5 to avoid overfitting and a train test split of 0.3. According to the validation scatter plot of our model, we can see that in most of the times the predicted values are quite close to the real values. Here's the visualization of the resulting tree. The tree has a depth of 5 and a number of leaf nodes of 18, and according to the weight of each feature in the tree, the feature importance is calculated and illustrated in the right graph. The most important feature is the 1 hour time lag price difference. This indicates that the price difference can be explained by the time lag feature of itself to a great extent. The prediction accuracy of the 3 models is compared in this graph. As we can see, both XGBoost and Random Forest significantly outperform the decision tree regressor. The XGBoost model has an R-squared of 0.84, outperformed the Random Forest model by 6.6%. The accuracy of negative values is also significantly higher. Now I will pass my time to my teammates to talk about the trading strategy and the backtest based on the model.
Thank you, Kellen. With 2 core models that have adequate performance, we will build a trading strategy and do backtest simulation to see how many returns the model can actually yield. First, let me introduce the initial setup in our simulation. The exchange A stands for Bitstamp Exchange, and exchange B stands for Bitflyer Exchange. We will hold the same amount of Bitcoin, 0.001 Bitcoin, and the same amount of cash, $5 at each exchange. The percentage of transaction fee at exchange A is 0.24% per order, and the one in exchange B is 0.02% per order. Here, we define our price difference as the market price in exchange A minus the market price in exchange B. The trading process is straightforward. There are only 4 main steps involved. We will mainly build our trading strategy on the XGBoost core model because it has a lower model complexity and generates output faster than the ARIMA LSTM model. Let me walk you through an example here. We first input historical data into our chained model, which output the predicted price difference for next hour. Dividing the predicted price difference by the current Bitcoin market price of exchange B, we get the price difference percentage. If the price difference percentage is smaller or larger than a preset threshold, we execute the arbitraging. In this example, the threshold is set as negative 0.01 because the price difference is negative. We set the threshold mainly to ensure that the model will not perform arbitraging when there is a narrow price difference. The arbitraging on these narrow price differences will not even cover the transaction fees. In this example, we can see the arbitraging is successfully executed. We earn $0.2 profit at the end. With above background knowledge, I will present our simulation result on negative price difference and positive price difference separately to you. For 1,771 hours testing period, our model and trading strategies gained a profit ranging from $297 to $1,251, depending on the preset threshold. The profit topped at threshold negative 0.002, after which it decreased. This is because with the threshold smaller than negative 0.002, the trading strategy performed arbitraging operation over many arbitraging opportunities that have a narrow price difference, which cannot even cover the commission fee. We also calculate the daily rate of return for each threshold. The highest daily rate of return in this case is 5.53%. In terms of the result on positive price difference, we can observe that the profit gained is rather marginal compared to the profit gained on negative price difference. The lower profit from the positive price difference is mainly because the number of large positive price difference is far smaller than the number of large negative price difference in this period. Despite of this, our trading strategy can still achieve a daily rate of return at 3% when the threshold is set to 0.008. Okay, now I will conclude our presentation with a bit discussion on limitations of our approach, and also further thoughts. As mentioned at the beginning, when we set the ask price during arbitraging, we have to consider the gaming among arbitragers, namely whether other arbitragers have a strong ability to execute orders quickly. Our model can give some implications on this. If the predicted price difference is closed very soon, we might assume that the arbitrager in the market might have a strong ability. However, to really incorporate this consideration in our model, we might have to explore the knowledge on price dynamics further. To conclude, in this project, we successfully implement two predictive models that take the fluctuations of the price difference into account. We also designed a trading strategy that utilizes the prediction result from the core model and combine it with considerations on commission fee to yield an attractive return. If you are interested in how we really implement models in detail, you could refer to our report. Thank you.